We're going to answer a couple of different types of questions here with this. So in this example, we are given the velocity vector of the particle. This is different because in the last example, we were given the position vector. So the velocity vector is obviously different information. So we're given the velocity vector and then we're told where the particle is at t equals 0. And we're going to use this information to answer a couple of questions. So we know where the particle is at t equals 0. How could we find the position of this particle at some time after that? What are we going to use? We're going to use an integral, right? And so if we integrate the velocity, remember the velocity is the rate of change of what? Position. So velocity is how fast the position's changing. If we integrate a rate of change, then we get the total change. You guys remember that? So we can use the integral to find the net change. So if we integrate a rate of change over a period of time, we figure out how much that value changes. So if I want to figure out what the x value is going to be at 4, let's just focus on the x value right now. So if I want to know what the x value is when t equals 4, I'm going to start with the x value when t equals 0, that's 1, and then I'm going to add on the change. So x has a value of 1 at t equals 0. I get that from this right here. And then I'm going to add on the change. How do I figure out how much it changes over that time period? I'm going to integrate what? T squared. So I'm going to integrate the x component of my velocity vector with respect to time, and I'm going to go from where to where? 0 to 4. Alright, so what we're doing here, I'm going to write this above it. This is x of 0. So that's the value of x at 0. And then we integrate from 0 to 4 to figure out what x is at 4. In fact, I'm going to write this using the same notation here. So we'll say that x of 4 is equal to x of 0 plus the definite integral from 0 to 4 of t squared. And we can evaluate this by hand. You should know how to do that. What do we do to evaluate this definite integral? Take the antiderivative, which is evaluate it from 0 to 4. So we get 1 plus, what is 4 cubed? 64. So it's 64 thirds minus 0. And so 1 plus 64 thirds is going to be what? Okay, that's going to be the x value at 4. How can I generalize that? Let's say that I don't care where the particle is at 4, but I just want to know where the particle is at any time. What could I do? No. Yes. If we put a variable in where the 4 is, let me just write this out here. I can find the x value at any t, at any time t, by taking the initial x value and then adding on the integral from 0 to t of, I'm going to have to use a different variable here. I'll use u squared with respect to u. Now, you guys understand why I had to use a different variable here? It's the same thing we did here, the t squared with respect to t, except I already have t as a variable here and I can't use the same variable in the limit and in the integral. And so what we would end up getting is going to be 1 plus t cubed over 3. And this is going to give us the x coordinate at any t value. So I can generalize this. We did it for 4, but I could generalize this for any t value just by using a variable upper limit here. We didn't ask to do that in this problem, though. We weren't asked to do it, so we don't need that. So how about y? How can we find the y value at 4? What do I start at? Start at the initial y value and then add on the definite integral from where to where? 0 to 4 of sine of pi t with respect to time. This one might be a little bit trickier, but I think we can do it. 3 plus, what is the antiderivative of sine? Negative cosine. And if I were to take the derivative of this, I would use the chain rule and I'd have to multiply by pi, right? So to counteract that, what do I need to do? I'm going to divide by pi. Everybody understand why I divided by pi there? So I put 4 in for pi. What is the cosine of 4 pi? 1. So I'm going to get negative 1 over pi plus, what's the cosine of 0? And so what do I end up with? 0, right? Well, is it 0?
3.
Yeah, it's going to be the 3. So this right here, these are going to cancel each other out. What's happening here when we go from 0 to 4 is cosine's going through 2 full periods. And so it's just getting back to where it started. Or actually, sine is going through 2 full periods, so we're getting back to where we started. So our y-coordinate is going to be 3. So what is the position of the particle at t equals 4? Should I write that as a vector or an ordered pair? Yeah, because it's just a point, right? So in part B, we're asked to find the total distance traveled by the particle from t equals 0 to 4. So we want to figure out how far it went going from this point here to this point here. How could we figure that out? How do we find total distance traveled? Which formula are we using? That's the arc length formula, right? So we're going to have the distance is equal to, it's going to be an integral, right? The integral from where to where? We know what the limits are going to be. 0 to 4. And we're going to integrate the square root of, what goes first? Dx dt. So do I need to take the derivative of t squared? No, why not? That is the derivative, right? So the velocity is the derivative of the position. So this is the derivative that I want to use right here. So we're going to have t squared plus sine of pi t squared with respect to time. This is not an integral that I'm going to ask you to evaluate by hand, so you can pull out your calculator and punch it in there. You want to make sure you're in the right mode here, and you should get about 21.964 for that total distance traveled. I'm not going to ask you to do this right now, but actually it wouldn't be bad. What is the distance between the starting point and the ending point? How far is it from 1/3 to 67 thirds 3? 64 thirds, which is about what? So a straight shot from the starting point to the end point is not much shorter than this. It's going to be 21 1/3. So this particle is not going too far off path here as it travels.